In 1940, a British bomber crew returned from a night raid over Germany. The aircraft's glass nose panel had shattered mid-flight. The bombardier survived only because fragments missed his eyes by inches. Within 2 years, nearly every Allied combat aircraft would abandon glass entirely. This is the story of polymethyl methacrylate, a transparent plastic that revolutionized aviation, saved thousands of lives, and reshaped post-war industry. Its trade names became household words: Plexiglas in the United States, Perspex in Britain, Lucite across commercial markets. But before it enclosed fighter pilots and bomber crews in curved, bulletproof canopies, it began as a laboratory curiosity with no clear application. Its path from chemical experiment to global standard spans decades of industrial development, wartime urgency, and Cold War transformation. Early aviation inherited its materials from ground-based industry. Aircraft designers in the 1920s and 1930s used the same soda-lime glass found in windows, automobile windshields, and greenhouses. For low-speed biplanes flying at altitudes below 10,000 feet, this presented manageable risks. Glass was heavy, brittle, and prone to thermal shock, but it remained the only transparent material available in industrial quantities. As aircraft performance improved, the limitations of glass became critical. Higher speeds generated aerodynamic forces that stressed rigid panels. Combat aircraft faced additional hazards: vibration from machine gun fire, impact from shell fragments, extreme temperature gradients between heated cockpits, and sub-zero external air. A single crack could propagate across an entire panel in seconds. Shattering glass inside a pressurized cabin or open cockpit endangered pilots, navigators, and gunners. Sharp fragments caused lacerations and temporary blindness. In winter operations over northern Europe and the North Atlantic, frost accumulation on interior glass surfaces obscured visibility entirely. Weight remained another persistent challenge. A typical bomber nose glazing assembly, comprising multiple flat glass panels set in metal frames, added hundreds of pounds to the aircraft's empty weight. This reduced payload capacity, climb rate, and fuel efficiency. Designers sought alternatives, but no existing material combined optical clarity, weather resistance, formability, and structural integrity at acceptable cost. The aviation industry needed a material that could flex without fracturing, tolerate rapid temperature changes, resist impact and abrasion, be molded into complex three-dimensional shapes, maintain optical clarity under ultraviolet exposure, and weigh significantly less than glass. No such material existed in commercial production before 1933. The chemical foundations of acrylic plastics emerged from European academic research in the late 19th century. In 1877, German chemist Wilhelm Rudolf Fittig synthesized methacrylate acid. Over the following decades, researchers explored various esters and polymers derived from this compound, but practical applications remained elusive. Early formulations were difficult to control, prone to discoloration, and lacked mechanical strength. The breakthrough came in 1928 at Röhm and Haas, a German chemical firm based in Darmstadt. Chemist Otto Röhm and his research team successfully polymerized methyl methacrylate into a stable, transparent solid. The resulting polymer exhibited remarkable properties: high light transmission comparable to optical glass, excellent resistance to weathering and discoloration, and the ability to be cast, molded, or machined. Röhm patented the process, and the company began small-scale production under the trade name Plexiglas in 1933. Parallel developments occurred in Britain. In 1932, chemists Rowland Hill and John Crawford at Imperial Chemical Industries independently synthesized polymethyl methacrylate and refined production methods suitable for industrial scaling. ICI introduced the material commercially as Perspex in 1934. In the United States, DuPont began manufacturing an equivalent product called Lucite in 1937, following its own research into acrylic chemistry. These early formulations required precise control of polymerization conditions. Temperature, pressure, catalyst concentration, and reaction time all influenced the final product's optical and mechanical properties. Manufacturers invested in specialized equipment and trained personnel to achieve consistent quality. Initial production volumes remained modest, measured in tons per year rather than the thousands of tons that would follow. Before aviation adopted acrylic glazing, the material found limited use in specialty applications. Dentists used methyl methacrylate resins for dentures and dental prosthetics, valuing its biocompatibility and ease of molding. Optical instrument makers experimented with acrylic lenses for cameras and scientific equipment. Architects and designers employed small sheets for decorative lighting fixtures and signage, attracted by its clarity and ease of fabrication. Manufacturing methods evolved rapidly during the mid-1930s. The earliest production technique involved bulk polymerization, in which liquid monomer was poured between glass plates and slowly heated. This process yielded flat sheets but offered limited control over thickness, uniformity, and internal stress. Cell casting, an improved method using precision molds and controlled heating cycles, produced higher quality sheets suitable for optical applications. Continuous extrusion processes emerged later, enabling faster production of standard profiles. Molding three-dimensional shapes presented distinct challenges. Unlike thermoplastic materials that could be repeatedly heated and reshaped, polymethyl methacrylate required careful temperature management to avoid degradation. Manufacturers developed specialized forming techniques: drape forming over heated male molds, vacuum forming against female molds, and pressure forming for complex contours. Each method demanded precise control of heating rates, forming temperatures, and cooling cycles to prevent crazing, warping, or optical distortion. Surface finishing posed another technical hurdle. Raw molded parts exhibited tool marks and microscopic surface irregularities that scattered light and reduced transparency. Polishing techniques borrowed from glass optics, progressively finer abrasives followed by buffing compounds, restored optical clarity but added labor and cost. Manufacturers invested in mechanized polishing equipment and trained specialists to achieve the surface quality required for aviation applications. By 1938, global production of polymethyl methacrylate reached several hundred tons annually. Rome and Haas dominated the German market, ICI controlled British and Commonwealth distribution, and DuPont served North American customers. Prices remained high, approximately 10 times the cost of equivalent glass by weight, limiting adoption to applications where performance justified expense. Military aviation authorities in Britain, Germany, and the United States began evaluating acrylic glazing in the mid-1930s. The Royal Air Force conducted initial trials in 1935, installing perspex panels in experimental aircraft to assess durability under operational conditions. Test results demonstrated significant advantages. Acrylic weighed approximately half as much as equivalent glass, absorbed impact energy without shattering, and maintained optical clarity after prolonged exposure to sunlight, rain, and temperature extremes. German aircraft manufacturers incorporated plexiglass into several pre-war designs. The Messerschmitt Bf 109, introduced in 1937, featured a frameless canopy with a single-piece acrylic windscreen that provided improved visibility and reduced aerodynamic drag. The Heinkel He-111 bomber employed acrylic nose glazing that could be molded into streamlined shapes impossible to achieve with flat glass panels. These early applications validated the material's suitability for military aviation and identified areas requiring further development. American aircraft designers followed similar paths. The Boeing Model 299 prototype of the B-17 Flying Fortress initially used conventional glass in its bomber nose. Later production models transitioned to acrylic panels that offered better optical quality and reduced vulnerability to shell fragment damage. Fighter aircraft, including the Curtiss P-40 and early variants of the Republic P-47, incorporated acrylic windscreens and canopy sections. Engineering challenges persisted. Acrylic's thermal expansion coefficient differed significantly from the aluminum alloy airframes to which it was mounted. Temperature changes caused dimensional mismatches that generated stress concentrations at mounting points. Designers developed flexible gasket systems and compliant mounting frames to accommodate differential expansion without cracking the glazing. Sealants and adhesives required reformulation to bond reliably to acrylic surfaces while tolerating fuel spills, hydraulic fluid exposure, and ultraviolet radiation. Optical distortion remained a concern for precision applications. Bombing and navigation required clear, undistorted visibility through large nose panels. Manufacturers refined molding techniques to produce complex curvatures with minimal thickness variation and internal stress. Quality control procedures included optical testing with interferometry and stress analysis using polarized light to detect defects invisible to the naked eye. By 1939, acrylic glazing had transitioned from experimental curiosity to proven aviation component. Production capacity remained limited, prices exceeded glass by a factor of 5 to 8, and fabrication techniques were still maturing. The material's full potential would only be realized under the extraordinary demands of sustained wartime production. The outbreak of war in September 1939 transformed acrylic glazing from specialty product to strategic material. Britain's Royal Air Force urgently needed transparent armor for bombers conducting daylight raids over occupied Europe. Germany required canopy materials for its expanding fighter force. The United States, preparing for potential conflict, identified acrylic plastics as critical to aircraft production. Production capacity expanded dramatically. ICI's Perspex plant in Britain operated continuously, with output increasing more than 20-fold between 1939 and 1943. Röhm and Haas in Germany prioritized plexiglass for military contracts, scaling production despite wartime shortages of raw materials and energy. In the United States, DuPont constructed additional lucite facilities while Röhm and Haas established American operations separate from its German parent. By 1943, Allied production of polymethyl methacrylate exceeded 20,000 tons annually. Manufacturing techniques evolved to meet demand. Continuous casting processes replaced batch methods, increasing output and improving consistency. Automated polishing lines reduced labor requirements. Standardized mold designs enabled rapid fabrication of common shapes, bubble canopies for fighters, nose sections for medium bombers, turret enclosures for heavy bombers. Manufacturers maintained extensive inventories of preformed blanks that could be trimmed and fitted to specific aircraft models. Quality standards tightened under operational necessity. Military specifications defined acceptable limits for optical distortion, impact resistance, weathering performance, and flammability. These specifications enabled interchangeability. Acrylic components from different manufacturers could be used in the same aircraft types. Inspection procedures included destructive testing of sample parts, accelerated aging trials, and field evaluations on operational aircraft. Rejection rates for out-of-specification parts reached 20% in some production runs, driving continuous improvements in process control. Aircraft designs increasingly exploited acrylic's unique properties. The B-17's chin turret used a molded acrylic dome that provided nearly hemispherical visibility for the gunner while maintaining structural integrity under aerodynamic loads. The consolidated B-24 Liberator featured an extensive acrylic nose assembly that eliminated metal framing and reduced weight by more than 100 pounds compared to glass equivalents. British bombers, including the Avro Lancaster, employed large acrylic panels in nose and tail positions, enabling effective defensive gunnery. Fighter aircraft adopted streamlined bubble canopies that maximized pilot visibility. The North American P-51 Mustang's Malcolm Hood, a retrofitted acrylic canopy replacing the original frame design, significantly improved rearward vision and became standard on late war variants. The Republic P-47 Thunderbolt's bubble canopy, introduced in the D model, exemplified the mature integration of acrylic glazing technology. These designs would have been impractical or impossible with glass. Maintenance procedures adapted to acrylic's characteristics. Unlike glass, which could be cleaned with abrasive compounds, acrylic required non-abrasive cleaners to prevent scratching. Field manuals instructed maintenance crews on proper handling, storage, and installation techniques. Repair procedures included heat-forming replacement sections and bonding patches over cracked areas using specialized acrylic cements. Production challenges intensified as demand escalated. Raw material supply, particularly methyl methacrylate monomer, became a bottleneck. Chemical plants producing the precursor compounds expanded capacity, sometimes at the expense of other polymer production. Transportation disruptions, labor shortages, and competing priorities for industrial resources all constrained output. Despite these limitations, acrylic glazing production met the essential needs of Allied aircraft manufacturing throughout the war. By the final years of the war, the vast majority of Allied combat aircraft incorporated acrylic glazing. The material's contribution extended beyond cockpit enclosures. Gun sights, instrument panels, navigation lights, and reconnaissance camera ports all utilized acrylic components. The wartime scaling of production capacity and refinement of manufacturing techniques created an industrial infrastructure that would define post-war applications. The end of hostilities in 1945 left acrylic manufacturers with massive production capacity and uncertain demand. Military contracts evaporated abruptly. Manufacturers faced the challenge of transitioning to civilian markets while preserving the industrial base and trained workforce developed during wartime. Commercial aviation became an immediate growth sector. Post-war airliners, including the Douglas DC-6, Lockheed Constellation, and Boeing Stratocruiser employed acrylic windows that provided passengers with clear, distortion-free views while reducing weight compared to glass. Pressurized cabins, standard on long-range transports, required glazing materials capable of withstanding sustained pressure differentials and thermal cycling. Engineers developed laminated and reinforced acrylic window assemblies that combined the material's optical advantages with structural designs addressing the unique demands of cabin pressurization. Acrylic's proven performance in military bombers provided the foundation for these civilian adaptations. Automotive applications expanded rapidly. Acrylic found use in instrument clusters, taillights, and decorative trim elements. Some concept vehicles and limited production sports cars experimented with acrylic canopies and windshields, though safety concerns and cost limited widespread adoption. The material's optical clarity and formability proved valuable for headlight lenses and reflector housings, applications that became standard across the automotive industry. Architecture and construction discovered acrylic's potential. Skylights, domes, and curtain wall glazing exploited the material's lightweight and resistance to impact. Designers appreciated acrylic's ability to be formed into complex, curved shapes impossible to achieve with glass. Large-scale applications included stadium roofs, shopping mall atriums, and industrial facility lighting. The material's excellent weathering resistance, maintaining clarity and mechanical properties after decades of outdoor exposure, made it suitable for long-term installations. Consumer products proliferated. Acrylic bathroom fixtures, lighting diffusers, point-of-sale displays, protective barriers, furniture components, and decorative items flooded post-war markets. The material's availability, ease of fabrication, and aesthetic qualities appealed to designers and manufacturers. Mass production techniques developed during wartime enabled cost-effective manufacture of consumer goods. Medical and scientific instruments continued using acrylic for specialized applications. Laboratory equipment, surgical instruments, dental prosthetics, and optical devices benefited from the material's biocompatibility, sterilizability, and optical properties. Acrylic's chemical resistance made it suitable for exposure to various reagents and biological fluids. Technological refinement continued throughout the 1950s and 1960s. Manufacturers developed modified formulations with improved impact resistance, higher temperature stability, and enhanced surface hardness. Abrasion-resistant coatings extended service life in demanding applications. Tinted and colored acrylics expanded design possibilities. Multi-layer laminates combining acrylic with other materials provided specialized performance characteristics. Production volumes increased exponentially. By 1960, global polymethyl methacrylate production exceeded 200,000 tons annually, more than 100 times pre-war output. Prices declined steadily as manufacturing processes improved and competition intensified. Acrylic transitioned from premium specialty material to commodity plastic available for routine applications. The industrial infrastructure created for wartime glazing production found new purposes. Precision molding equipment designed for fighter canopies manufactured consumer electronics housings. Optical polishing facilities that finished bomber nose sections produced camera lenses and display screens. The technical knowledge and manufacturing expertise developed under wartime urgency became the foundation for an entire segment of the plastics industry. Polymethyl methacrylate's trajectory from laboratory synthesis to global commodity material illustrates several recurring patterns in industrial development. A fundamental scientific discovery, Rum's polymerization process, required 2 decades of engineering refinement before practical applications emerged. Early adoption by military aviation drove rapid scaling of production capacity and manufacturing expertise. Post-war transition converted military-funded infrastructure into civilian industrial capacity. The material's technical characteristics enabled design innovations across multiple industries. Aviation progressed from framed glass panels to streamlined bubble canopies because acrylic's formability permitted shapes impossible with glass. Architecture exploited acrylic's lightweight and impact resistance to create structures that would have been impractical or prohibitively expensive with traditional materials. Consumer products incorporated acrylic because mass production techniques made it economically competitive with existing alternatives. Acrylic's wartime role illustrates the complex relationship between military requirements and technological advancement. The urgent need for shatter-resistant aircraft glazing accelerated development timelines, justified capital investments, and motivated engineering solutions that might not have emerged under peacetime market conditions. The resulting production capacity and technical knowledge became post-war assets available for civilian applications. Environmental and safety considerations eventually constrained some applications. Acrylic's flammability and smoke generation during combustion led to restrictions in certain building codes. Automotive safety regulations favored laminated glass windshields over acrylic alternatives. Material recycling challenges associated with thermosetting polymers raised sustainability concerns. These limitations drove continuing research into improved formulations and alternative transparent polymers. Yet polymethyl methacrylate remains in widespread use more than 90 years after its initial commercialization. Modern applications range from protective barriers in public spaces to lighting fixtures, signage, aquarium viewing panels, and optical fiber components. The material competes with polycarbonate, tempered glass, and other transparent materials, each offering distinct advantages for specific applications. The industrial ecosystem that developed around acrylic production, chemical suppliers, molding specialists, finishing operations, distribution networks, represents a permanent expansion of manufacturing capability. This infrastructure supports not only acrylic products, but adjacent polymer technologies, tooling innovations, and process refinements that benefit the broader plastics industry. The development of polymethyl methacrylate from academic curiosity to strategic material to ubiquitous commodity spans nearly a century. Its initial commercialization in the 1930s addressed niche markets in dentistry and optics. Aviation's adoption in the late 1930s demonstrated the material's potential for demanding applications. World War II production requirements scaled manufacturing capacity by 2 orders of magnitude and refined fabrication techniques to industrial maturity. Post-war transition converted military-funded infrastructure into the foundation for diverse civilian applications. Acrylic glazing solved a critical problem in military aviation, the fragility and weight of glass in high-performance aircraft. But its long-term significance extends far beyond wartime utility. The material's combination of optical clarity, formability, lightweight, and weather resistance created opportunities for innovation across aviation, architecture, automotive design, and consumer products. The manufacturing expertise and industrial capacity developed to meet wartime demand became a permanent asset that enabled post-war economic development. This pattern, fundamental research, niche commercialization, military-driven scaling, post-war civilian expansion, recurs throughout the history of materials technology. Polymethyl methacrylate's trajectory exemplifies how urgent wartime requirements can accelerate technological maturity and create industrial capabilities that persist long after the originating conflict ends. The transparent canopies that protected fighter pilots and bomber crews in 1944 were one application of a material whose influence ultimately reached far beyond the battlefield. That same chemistry now encloses commercial aircraft passengers, illuminates urban environments, and appears in thousands of everyday objects. The industrial transformation that began with a search for shatter-resistant aircraft glazing reshaped manufacturing, design, and daily life across the global economy. Watch next to see how a rubber shortage in wartime Germany forced vehicles to switch to wooden and steel wheels.